Let's solve some electromagnetism physics revision questions. As always, the links to these questions are in the description of the video, and this video is best tackled by solving the questions first and then checking in with my solutions. So, first question, define magnetic flux. So, magnetic flux is defined as BA cos theta. Therefore, the magnetic flux is the product of B, which is the magnetic flux density. So magnetic flux density. And now it's not just any area, it is the perpendicular area as indicated by this angle cos theta. So, and the perpendicular area. Okay, next one, part B. Figure 4.1 shows a generator coil of 500 turns and a cross-sectional area of 2.5 times 10 to the power of -3 cubic meters. We've got the magnetic flux density 0.035 Tesla. The plane of the coil is perpendicular to the magnetic field. Okay, so if the plane of the coil is perpendicular to the magnetic field, this means that the angle theta is actually going to be 0, because in this equation here, theta is the angle to the normal. In other words, if I have an area like this, and let's say that this here is the magnetic field, then this here is the angle theta. So as soon as this line becomes perpendicular and it's along the normal, the cos component will turn to 1. Okay, calculate the magnetic flux linkage for the coil in this position. Give a unit for your answer. So phi will be equal to NBA cos theta, which is going to equal to n, which is 500. Let's multiply by b, which is 0.035. Multiply by the area, which is given 2.5 times 10 to the power of -3 standard units. 2.5 times 10 to the power of -3. So because the angle is 0, I'm just going to write times cos of 0 degrees, which is of course just equal to 1. And this will be equal to about 0.044, and the unit for that is Webers. Okay, next one. The coil is rotated about the axis in the direction shown in the figure above. So that's figure 4.1 just here. So this thing is getting rotated around this axis. And figure 4.2 shows the variation of the flux, magnetic flux against time t, which is changing, of course. Explain why the magnitude of the flux for the coil varies. Well, there's two things. First of all, the component of the flux density, which is perpendicular to the area, changes. It is maximum when B is perpendicular to the area and 0 when B is parallel to the area. So essentially when the area is perpendicular, this corresponds to this. So this is maximum flux, and this over here is 0 flux when it is parallel to the area. This figure here will kind of look like this. Imagine this is your coil, then the field will be, let's say, going in like that. However, if this is rotating so that it goes up here, it might look like this, where this is your area, and then the field goes like this. And in this case, this will be parallel, and this will correspond to a flux of 0. So part II, state Faraday's law of EM induction. This keeps appearing again and again. The induced EMF is proportional to the rate of change of magnetic flux linkage. It's really important that we use the word rate of change. Use the figure to describe and explain the variation with time of the induced EMF across the ends of the coil. Okay, well, let's use this figure. So first of all, we need to mention that because of Faraday's law, the induced EMF is actually the gradient of this graph. Now, if the induced EMF is the gradient, think about it, the gradient here is 0 because the gradient of the tangent here is just a flat line. The gradient here is also 0. Let's draw this properly. There's 0 here, it'll be 0 there. It will be greatest, it will be at its steepest in this position right over here when the line actually crosses the x-axis. Now, because of that, here's how I formulated the answer. The EMF is the gradient of the graph, and this is really, really important. It is a maximum when phi is equal to 0, and that happens at those times. The EMF is 0 when the magnetic flux is a maximum, and this happens at those appropriate times. Okay, part 4, use figure 4.2 to determine the magnitude of the average induced EMF for the times between 0 and 0.005 seconds. So we're just going to use Faraday's law, and I'm going to say that the induced EMF is just equal to the rate of change of the magnetic flux linkage. So that's going to be n phi over delta t. Now, how does the magnetic flux change between those 2 points? At this point here, the magnetic flux is just 0. I'm going to take the maximum one, which is just going to be n, which is 500, multiplied by BA cos theta. So what is that going to be? 0.035 Tesla multiplied by 2.5 times 10 to the power of minus 3. I'm going to divide that by delta t, which in this case is just 0.05. If we put that into a calculator, the two minus signs are going to cancel, and this should give us, let's see, 8.75 volts. Okay, question 5, state and explain. So we have two command words, both to state and explain the effect on the magnitude of the maximum induced EMF across the ends of the coil when the coil is rotated at twice the frequency. Okay, well, the EMF will increase by a factor of 2. So we can write this down. The EMF will increase by a factor of 2. So we've done the state part. Now let's explain this. How can we explain this? Well, remember, just as an aside over here, I'm going to write that EMF is equal to minus delta n phi over delta t. So if you're increasing the frequency, you're actually decreasing the time period. And if the time period in a way goes down, the rate of change increases, meaning that the induced EMF will increase by that factor. So we could probably just say that the rate of change of magnetic flux linkage doubles. Okay, next one, figure 3.1 shows part of an accelerator used to produce high-speed protons, and they're shown over here. They are in a field, they produce a circular orbit. So the radius is r and a magnetic flux density b. State clearly the direction of the magnetic flux density b that produces the circular motion of the protons. Now, using the left-hand rule, Fleming's left-hand rule, the direction of the flux density b is out of the page. I'm going to write this very clearly, out of the page, and just in brackets over here I'm going to write Fleming's left-hand rule, just so you guys know how to get this. Show the relationship between the velocity v of the protons and the radius is given by the following expression, where q and m are the charge and mass of a proton respectively. Okay, well, And because this object is moving in a circular motion, we can set the magnetic force, which is QVB, to be equal to mv squared of r. We can cancel out those v's, and rearranging for v, we're going to get that v is going to equal to QBR, or in this case the radius is actually given by capital R, so let's change that. Divided by m, which is the expression that they were looking for. C. Calculate the magnetic flux density B of the magnetic field needed to keep the protons in a circular orbit of radius 0.018 meters. The time for one complete orbit is 2.0 times 10 to the power of -8 seconds. Okay, well, let's calculate the time for one complete orbit is just the time period, so we can calculate the speed, because this will just be equal to 2 pi r divided by the time period, which will be 2 pi times 0.18. I'm going to divide that by 2.0 times 10 to the power of -8. Let's put this into a calculator. And that's approximately equal to 5.65 times 10 to the power of 7 meters per second, which is a pretty high speed. Okay, now let's rearrange the above equation because we're looking for the flux density. So B, I'm just going to rearrange this equation essentially, will just be equal to V times m, and then we're going to divide by QR. So we have the speed, which is 5.65 times 10 to the power of 7. Now, because this is a proton, we need to write in the mass of a proton, which is just 1.67 times 10 to the power of -27. Now let's divide that by the charge, which is 1.6 times 10 to the power of -19, and the radius, which is 0.018. Oops, we've got a little mistake. Let's just correct that. So the radius, of course, is 0.18 meters. And let's plug this into a calculator now, which is going to give me a value for B to be equal to 3.276. So let's go at 3.28 Teslas. Okay, part D, explain why the magnetic field does not change the speed of the protons. This one here is a classic question. So the force is perpendicular to the velocity. Perpendicular to the velocity. We could also write displacement rather than velocity. Therefore, no work is done, and hence the speed doesn't change. So, next question. Part 1, define electromotive force or EMF. Remember, EMF is energy transferred from other forms to electrical energy per unit charge. Once again, to define the magnetic flux, it is the product of the magnetic flux density and the area that is perpendicular to the field. Part C, figure 1.1 shows a simple transformer. Now it's a really important question. So the primary coil is connected to an AC power supply. Explain how an EMF is produced in the secondary coil. So our first marking point that there is a changing magnetic flux linkage in the first coil. This is due to the fact that there is an AC current going through it. If the current is changing, this means that the magnetic field around the wires is changing, means that there's a changing magnetic flux linkage. The iron core then links this flux to the secondary coil, and the changing magnetic flux linkage in the secondary coil induces an EMF. So this means that, I don't know, here we could, I don't know, maybe put something like a light bulb or something like that, and this would mean that we will measure some PD across it. But this standard answer here with those 3 points will always give us the relevant marks on a question on transformers. Just a little note that I won't be solving the rest of the question because it's significantly easier, but I did really want to solve this part. If you had a go at the next part, I'll post a link to the mark scheme in the description. Okay, next one, starting off with the classic of stating Faraday's law. Remember, the induced EMF is proportional to the rate of change of magnetic flux linkage. Now, part B, figure 5.1 shows a magnetic or a magnet being moved towards the center of a flat coil. So we have a flat coil, we have a moving target, a current is induced in the coil. Use ideas about conservation, energy conservation to state and explain the polarity of the face of the coil nearer to the magnet. Well, if this here is a north pole, this here will also be a north pole. So let's just state that first of all. So this here is the will have to be a north pole. So I've done the first bit, which is to state. Now let's actually explain this. Why would that be? Well, imagine if this was a south pole. So if this for some reason was a south pole, so let's just write if the face was a south pole, well, those two will attract. So imagine that this thing is a south pole. If that's the case, they will start attracting each other and there will be a gain in kinetic energy, which is impossible because we would have gained energy out of nowhere. So if this was a south pole, there will be a gain, will be a net gain in kinetic energy, which is not allowed by the conservation of energy. And this is why this face here has got to be a north pole. Okay, part C, figure 5.2 shows the magnetic field from a north pole of a vertically held bar magnet, and we have some coils over here, but crucially this question is asking us explain why there's no induced EMF across the ends of the coil. No matter the situation, the only explanation of this is that there is no change, the zero rate of change of magnetic flux linkage. So we can say that there is no rate of change of magnetic flux linkage, because the only thing that actually causes an EMF is a change in the magnetic flux, and if this isn't happening, well, we have no EMF. Okay, next one we've got figure 5.3 is a graph showing how the magnetic flux density varies along a horizontal line. So here we do have a change. We can see that the flux density is going up, then it's relatively constant, then it's going down. And what we need to do, I guess, is to convert that to an EMF graph. So the same small flat coil is moved at a constant speed from X to Y. The plane of the coil remains horizontal between X and Y. On the axis provided, sketch a graph to show the variation of the induced EMF across the ends of the coil with distance from X. Now, as we are moving it in this region of a field, well, the induced EMF will be 0 if there's no field. So we should start off with the EMF being 0 pretty much all the way up to here. Now, if the magnetic flux density is constant, so that's between 5, so between here, let's be quite careful, and where else is 0? Oops, and let's be a bit more careful, and 8. So between those two lines it will also be equal to 0. So it will be along here. Now I'm expecting the EMF to essentially jump between here and then here. But also have a look, because the EMF is the gradient of the change of the magnetic flux. If the gradient has opposite signs, then the EMF will also have opposite signs. So let's say that here the gradient is positive. I'm kind of expecting a pulse like this, and then a pulse such as this one before the EMF is 0 once again. So here the EMF is 0, also here, where else? Also here as well. Now we're asking just to sketch a graph, so we don't need to worry about actually the calculation of this value. Okay folks, well, I'm hoping that this video was very, very useful. Don't forget, you need to revise the whole of electromagnetism, and check out this video in which I go through the whole of electromagnetism, and hopefully you'll find that useful and ace the exams.